Welcome to Ask Prep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of physics, which is fluid mechanics, Bernoulli's theorem and viscosity. Fluids, unlike solids, have the ability to flow and adapt to the shape of their container. In physics, fluid mechanics helps us understand the behavior of liquids and gases in motion. One of the fundamental principles governing fluid flow is Bernoulli's theorem, which establishes a relationship between pressure, velocity, and height in a moving fluid. This principle plays a crucial role in various real-world applications, from aviation to medical science. To understand Bernoulli's theorem, imagine a fluid moving through a pipe with varying diameters. As the fluid moves through a narrow section, its speed increases, and consequently, the pressure decreases. This relationship, derived from the conservation of energy, states that the sum of the pressure energy, kinetic energy, and potential energy per unit volume remains constant along a streamline. Essentially, where a fluid moves faster, the pressure is lower, and where it moves slower, the pressure is higher. This principle explains why airplanes generate lift. The shape of an airplane wing, or airfoil, is designed so that air moves faster over the top surface than underneath. Due to Bernoulli's theorem, the pressure above the wing is lower than below, creating an upward force that allows the plane to lift off the ground. The same concept is applied in the working of carburetors, atomizers, and even in the human circulatory system, where blood flow is influenced by pressure variations. While Bernoulli's principle is useful in understanding ideal fluid behavior, real-world fluids also experience resistance to motion. This resistance is due to viscosity, which is a measure of a fluid's internal friction. Highly viscous fluids, like honey or oil, flow much slower than less viscous fluids, like water or air. Viscosity plays a crucial role in determining the flow rate of a fluid through a pipe, the movement of oil in an engine, and even the circulation of blood in our bodies. Viscosity depends on the cohesive forces between fluid molecules. In liquids, viscosity decreases with increasing temperature because the molecules move more freely. In gases, however, viscosity increases with temperature, as higher energy levels lead to more frequent collisions. Understanding viscosity helps engineers design efficient lubrication systems, improve medical treatments, and develop better industrial processes. One of the important observations related to viscosity is Poiseuille's law, which describes how the flow rate of a viscous fluid through a tube depends on the tube's radius and the applied pressure difference. This principle is widely applied in medical sciences, especially in understanding blood flow through arteries and veins. If an artery narrows due to plaque buildup, the resistance to blood flow increases, affecting circulation and leading to potential health issues. Similarly, in industrial applications, engineers design pipelines keeping viscosity in mind to ensure smooth and efficient transport of liquids. When discussing fluid mechanics, it's also important to consider the difference between laminar and turbulent flow. In laminar flow, fluid moves in smooth layers without disruption, while in turbulent flow, chaotic eddies and vortices form. The transition between these two types of flow is determined by the Reynolds number, a dimensionless quantity that depends on fluid velocity, viscosity, and pipe diameter. Understanding this concept helps scientists and engineers optimize designs for vehicles, aircraft, and even water supply systems. In the field of medicine, the principles of fluid mechanics and viscosity are applied in designing medical devices such as syringes, foredrips, and respiratory support systems. For instance, the correct selection of fluid viscosity ensures that medicines are administered at the right flow rate. Similarly, in industries, lubricants are selected based on their viscosity to reduce friction and wear in machinery. Fluid mechanics also plays a key role in natural phenomena. Ocean currents, wind patterns, and even the weather system are influenced by the movement of fluids. Understanding these processes helps meteorologists predict storms, oceanographers study marine ecosystems, and engineers develop better water management systems. One fascinating phenomenon observed due to Bernoulli's principle is the Venturi effect, which describes how a fluid's velocity increases and pressure decreases when passing through a constricted section of a pipe. This principle is widely used in medical oxygen masks, where a high-speed stream of oxygen draws in ambient air, providing an effective oxygen supply to patients. Similarly, in the automotive industry, fuel injectors operate on the same principle. By creating a pressure difference, they efficiently mix fuel with air for combustion, improving engine performance and fuel efficiency. In everyday life, we also see the applications of Bernoulli's principle in sports. For example, in cricket, when a bowler imparts spin on the ball, the variation in airflow speed on either side creates a pressure difference, causing the ball to swing in midair. Despite its widespread applications, Bernoulli's theorem is based on the assumption of an ideal fluid, meaning it does not account for viscosity, turbulence, or external forces like friction. However, in real-world scenarios, fluid flow is often influenced by these factors. That's why engineers and scientists use modified equations that incorporate viscosity and turbulence to achieve more accurate predictions and designs. Understanding the principles of Bernoulli's theorem and viscosity is crucial not just for physics but for various fields of science and engineering. From designing airplanes to improving medical treatments, from predicting weather patterns to optimizing industrial processes, these concepts help shape the world around us. As we continue to explore fluid mechanics, new innovations and discoveries will further enhance our ability to manipulate and utilize fluids for the benefit of society. By mastering these concepts, students can gain a deeper appreciation of the fundamental forces governing fluid behavior, paving the way for future advancements in technology, medicine, and environmental science. The study of fluid mechanics is not just a theoretical subject, it is a practical tool that influences our daily lives in ways we may not even realize. So the next time you see an airplane taking off, a river flowing, or even a simple spray of perfume, remember that the principles of Bernoulli and viscosity are at play, shaping the world in dynamic and fascinating ways. Thank you. This is Ask Prep, your guide to mastering NEET preparation. Let's decode complex topics and simplify your journey to success.